Integration by partial fraction is to take integral that is a rational function. So for example, if we've got an integral of a function f at x over g at x and d at x. So it's some kind of a polynomial at the top, some kind of polynomial at the bottom. Then what you can do is you can factor this out. So factor the bottom into smaller pieces. So factor means putting them into forms of multiplication. So in this case, we will have multiplication of some sorts. And at the top, you will still have f at x for now. So what you will do is, say for example, we've got like ax plus b, cx squared plus d, and ex plus, well, h to the power of 2. Say something like this. So this was able to be factored into this form. Then what you want to do is you want to assign variables called like a, b, c, d, e. They use capital letters, but you have to know for the powers though. Sometimes you have something to the power squared, but with addition, so you cannot factor anymore. And sometimes you have more than one power, like this. So in this case, assigning up capital letters a, b, c, d, e in the numerator to break this apart. So this is where capital letters are assigned to break it apart. Sort of there's rules to follow when it comes to these different powers or the different order. So in this case, you will just take this expression and then you'll be expanding it out here. So in this case, we will have ax plus b over a. So knowing that for any fractional expression, the numerator is going to be 1 power less than the denominator. If it is the same power, then you can actually split it with a whole number, meaning the quotient, with the remainder. So remainder is always 1 power less, at least 1 power less. And plus, here we've got x to the power of 2. So we need to capture every possibility. That's why the next letter will be b, but we need to put x there. If b is 0, that's okay, but we need to still, b could not be 0, so we need to capture every possibility. And then we have capital C. So any kind of a linear form, which is 1 power less than this, and we will have cx to the power of 2 plus d. And then at last, we've got 2 powers. So this is actually ex plus h. There's a possibility for this. And you need to also consider ex plus h to the power of 2, because after all, this is raised to the power of 2. There's 2 of them. So in this case, you will have, the next letter will be e over ex plus h, and the other one will be, say, f, ex plus h to the power of 2. So what you'll be doing is, in order to bring this all together, you need to multiply this by this and this and this. You need to multiply this by this and this. Actually, you need to multiply this only by these two, because this is already capturing the power of 2. And then when it comes to this factor, so when it comes to this factor, you need to multiply by the yellow underline. When it comes to this factor, you need to multiply by this and this. And when it comes to e, you need to multiply by this, this, and one more term of that. And when it comes to f, you need to multiply by everything else. And so you'll be laying out systems of equations and simultaneously be working out to solve for a, b, c, d, e. Then once you've done that, you can expand the integral out as a over ax plus b plus bx plus c over cx squared plus d plus e over ex plus h plus f over ex plus h to the power of 2, and this whole thing over dx. So usually in this case, this is a linear form, and that looks like derivative of ax plus b. So you will have to account for this a factor, and you will be using ln. So that can be translated as, let's continue here, say a times ln ax plus b. The reason why we put absolute value is because it's linear, which means it can be negative sometimes. And if we were to take derivative of this, then we'll have a factor of a, which means we need to offset by factor of a. And then the next one will be, well, it depends on how you can solve it, but there are many different ways. Depending on the combination of b and c, sometimes you can just apply ln if they're in relation to one another, or sometimes you can use the concept of arctangent. So the equation, if you have anything of form of 1 over x squared plus a squared dx, we know that that is equal to 1 over a arctangent of x over a plus c. C just to show that it's a general case. To prove arctangent, say that tangent inverse x over a is equal to y. That means tangent y is equal to x over a, because this is inverse, they switch. And if you were to take derivative of both sides implicitly, then you will have secant squared y dy over dx, which is equal to 1 over a. So that means dy over dx, which is derivative of the initial thing that we want to take derivative of, then that will equal to 1 over a times 1 over, because you were both dividing both sides by secant squared y. And that is equal to 1 over a times 1 over 1 plus tangent squared y. But we know that tangent y was equal to this. So that will equal to 1 over a times 1 over 1 plus x squared over a squared. So this a squared can come to the top. You can merge the bottom. So you will have 1 over a squared plus x squared, and one term of this will cancel out. So you will have a over a squared plus x squared. So if you have something like this, you need to just offset for this extra term of a by dividing it by this. So just like what we do here. So this equation is useful when you just have a number at the top, no variable, but you have addition of two different squares. So depending on how this looks, you may have to apply the arctangent. This is also known as arctangent. They're exactly the same expression, and so forth. You will have to take the antiderivative using various different techniques that you know so far. So this is basically integration by partial fractions, which solves the integral of rational functions.